The width of this structure is 50 microns. That is a width even thinner than that of a hair. Furthermore, the structure has wiring that is even thinner. It is a nanoscale semiconductor circuit. Basic Research Laboratories is making full use of semiconductor nanofabrication techniques to create these fine structures. The goal is to feel the force of nanosize. The mechanical structure shown here is a cantilever. One end of the plate is fixed, and the other end moves up and down with deflections. Cantilevers are used in devices such as AFM probes. From the deflections, they detect surface profiles in atomic size. Currently, mainstream AFM reads the size of deflections from a laser's beam's degree of reflection. Therefore, several optical components are needed. If a cantilever has nerves that can sense deflections, then the entire apparatus can be assembled on one chip. We have created nerves for cantilevers using semiconductors and superconductors. This cantilever has a semiconductor circuit as shown here. A magnetic field is applied perpendicularly. Electrical current flows and the resistance is measured. When the magnetic field increases, the resistance fluctuates repeatedly. This phenomenon is called the quantum Hall effect. By fixing the magnetic field when the change in resistance is steep, an extremely strong charge in resistance can be seen in the response of the cantilever to deflections. By making use of this phenomenon, the size of deflections can be detected with great sensitivity. Next, on this cantilever, two superconductor niobium electrodes having a gap are placed on the indium arsenide layer. When the cantilever is cooled to ultra-low temperatures, a supercurrent flows from one piece of niobium to the other. By increasing the current, at some point the superconducting state is broken and resistance occurs. By fixing the current at this threshold value, an extremely strong change in resistance can be seen in the response of the cantilever to deflections. Making use of this phenomenon, we are able to detect the size of deflections with a high sensitivity. By making the cantilevers even smaller, it will be possible to create new devices that can detect electron spins. In due time, it might just be possible for nanocantilevers to read and write qubits.